Do I have to admit or you will be admitting?
I'll admit.
Should I start?
So do you have any PPT or anything, sir?
No.
Nothing.
No.
It's simply introduction.
You can ask in case they want, I may. Otherwise, it's not.
Okay, sir. You can ask them to switch on their camera, sir. So
Okay.
that you have a nice introduction.
Okay. So good afternoon. How many are there? Good afternoon, everyone. So welcome to this fourth live session. And if you have any question, you may ask, and you may even switch on. Switch on your camera so that we can interact like live. So please go ahead with your questions. If you have any question, please.
Good afternoon, sir.
Yeah, good afternoon. Yeah. Shiva.
Sir, yes, sir. Yes, sir. I'm Shiva Bhagat, sir. Sir, can you elaborate about from the first session, the basic stress strain, 3D stress strain?
Could you please repeat? Somehow. Can you please repeat?
Sir, about the matrix, the 3D stress strain matrix. Yes.
What is the doubt there regarding 3D stress strain matrix?
Can you just give a brief thing, sir? How it's formed, like that?
I mean, how stresses are related to strains. Three-dimensional stress strain relationship. See, I think I have started with isotropic because it is easy to understand, and then I think I have actually extended this to orthotropic. Okay, so maybe could I write? I'll just share my screen and see what okay. I have done that, but again because yeah, I just. Okay, otherwise I can give my I can show.
Do you want to write in whiteboard, sir?
Yeah, otherwise I can show my lectures also. I think that is lecture 3, lecture 4 maybe. Just my lectures are there, no? Just now I saw the lectures. Okay.
If you want. You have your PPT here, sir?
Yeah.
Okay.
You can share this. Hello. Hello, Shiva.
Yes, sir.
Yeah, just see. I think my screen is visible. Basically, the 6 components of stresses are related to 6 components of strains. Okay, sigma x, sigma y, sigma z, tau xz, tau yz, tau xy. Sorry, is related to the corresponding strains. I think you understand what are those 6 components of stresses and strains. Okay, epsilon x, epsilon y, epsilon z, gamma xz, gamma yz, and gamma xy. So this is C11, C12, like this up to C16, C12, C22, C26, C16, C26, C66. Now, before going to orthotropic, I think I have given some idea what is that exactly. Without this actually comes from generalized Hooke's law, where the 6 components of stresses could be expressed as a linear combination of 6 components of strains and vice versa. But before going to that, you could actually physically see, if you, because all of you know this, therefore it is easy to understand what exactly these elements of this matrix are. Suppose this is your X, Y, and say Z. So suppose this is subjected to sigma X. As you know that in one plane, there could be 3 stresses. Is that clear? 1 normal stress and 2 shear stresses. You know that, right? So this is X plane. So normal stress is sigma X. You have tau XY and tau XZ. Similarly, in all the 3 planes, you have 3 stresses, 1 normal and 2 shear stresses. So how they are related? Now suppose this is only subjected to sigma X. Suppose you consider this object and it is only subjected to sigma X. Okay. The material property is Young's modulus is E and Poisson's ratio is nu. Can you tell me what is the strain along X? Epsilon X is equal to by
minus
sigma X divided by
X.
Sigma X divided by E. Is that okay?
Yes, sir.
Fine. Is that clear?
Yes, sir.
Okay.
Yes, sir.
Now, suppose we also subject these two, sorry, we subject this to sigma Y also. So because of this sigma Y, what will be the strain along Y? That will be sigma Y by E. Is that clear? Okay.
Yes, sir.
Similarly, this is also subjected to say sigma Z along Z. Therefore, there will be normal strain along Z, epsilon Z, which is nothing but sigma Z by E. Up to that, it is clear, right? Now, when we apply a stress sigma X, in addition to having, because of this strain along X, it also produces strain along Y and Z. Why? Because of Poisson's effect. You know that, right? So what is the definition of Poisson's ratio? Poisson's ratio nu is equal to epsilon Y by epsilon X if only sigma X is applied. I'm just writing it for isotropic. I'm not writing for orthotropic so that you understand it. Okay. So what is epsilon Y? Therefore, epsilon Y is equal to nu into epsilon X. Okay. That means nu into sigma X by E minus. Therefore, this is because of sigma X, there is also a strain along X that is equal to minus nu sigma X by E. Is that clear? Is that clear? Okay. Similarly, because of sigma Y, there is also a strain along X because of Poisson's effect. That is sigma nu sigma Y by E. Is that clear? Similarly, because of Y, there is also, because of Z, there is also a strain along X, which is nu sigma Z by E. Okay. Similarly, because of Z, there is also a strain along Y, which is nu sigma Z by E. Similarly, along Z, because of X, there is nu sigma X by E. Because of Y, there is nu sigma Y by E. So we get, because of the 3 normal stresses, sigma X, sigma Y, sigma Z, what are the strains along X, Y, normal strains? Is that clear? Is that clear? We can add them because it is in the linear elastic regime. Therefore, we can superpose this. Initially, we started that as if only sigma X is acting alone, only sigma Y is acting alone, only sigma Z is acting alone. When they act simultaneously, we can add their responses. So this is the normal strain. Okay. Similarly, what is the shear strain? gamma xz is equal to tau xz by g. Gamma yz is equal to tau yz by g. Gamma xy is equal to tau xy by g. So when we rearrange them in matrix form, we can write it like this. Sorry, epsilon x, epsilon y, epsilon z, gamma xz, gamma yz, gamma xy. We can write in matrix form is equal to, just see, 1 by e minus nu by e minus nu by e, 0, 0, 0, sigma x, sigma y, sigma z, tau xz, tau yz, tau xy. Similarly, here also it is nu by e, 1 by e minus nu by e, 0, 0, 0, then minus nu by e, minus nu by e, 1 by e, 0, 0, 0, 0, 0, 0, 1 by g, 0, 0, 0, 0, 0, 0, 1 by g, 0, 0, 0, 0, 0, 1 by g. So this is what is the stress strain relationship in 3 dimension. Now this is nothing but the S.
Not audible, sir. Hello. Not audible, sir.
Muted. Hello. Hello. Am I audible?
Okay.
So yeah, Shiva, is that clear?
Fine, sir. Fine, sir.
Yeah. So
Sir,
if you are still, yes.
This is for isotropic materials.
Yes. Now for orthotropic, I told you it is easy to make you understand so isotropic. Now only thing is when you write the strains because of the Poisson's effect, you have to be careful in writing nu xy when it is stress is applied along x and we are finding out the strain along y. Nu xz when the stress is applied along x and the Poisson's, I mean the strain we are trying to find out along z. So that is the only difference. So and then ex, uy, ez, gxy, gyz, zx. Otherwise, the philosophy is exactly same. I have that is there in your slide. If you are still not clear, we'll have one more live session. You can repeat it again. I'll do that for orthotropic also, because I think I'll take other questions also now.
Okay, sir. Okay. Thank you.
Yeah. Any other question?
Good afternoon, sir.
Yes, Satendra, please.
Yes. Actually, it's some internet problems. I cannot listen after turning my camera. May I ask some question without turning on my camera?
Sure. Please go ahead.
Thank you, sir. Actually, the way you have explained the things in the lecture, that was very good. So I have no doubt regarding that part. So if you allow, may I ask some question related to the exam pattern?
Please ask.
Okay, so sir, I'm going to ask 3 or 4 questions. If you
Please.
think that you can share here, then please say yes. Otherwise, you can say no. Actually, I'm a PhD scholar, so I'm very serious about this course. So I'm going to ask.
Yeah, please.
Yes. First question, sir. Actually, there is some percentage criteria of theory or numerical portion in exam, like 40 or 60% will be numerical and 30% will be theory, like that.
No. It's objective type. Okay. Basically, it's so even if it is numerical, you'll have to choose the correct answer. That's all. Okay, and
yes,
please make sure.
yes,
I have already told in the last. I think somebody else asked. This examination is basically to understand how much you understood the mechanics of composite material, not about finding out inverse of matrix, not about finding out other things. So rest assured that you don't have to do those things in the exam hall. Okay.
Okay. This is my first session that I am attending because of the some regular classes in my PhD work. So I didn't not able to join your live session. So I don't know that this types of doubt has been clarified by you or not. So it's my first session. That's why I'm asking.
Yeah, please. Yeah. So if, regarding exam, your that screen calculator is good enough. So I mean that is what the directive is. Okay. So questions will be like whatever calculations are there, minimum that the screen calculator will be good enough. Okay.
Okay. So yes, that was my second question. Inverse related problem. You have shared that there will be no inverse type problem. If there is something.
This is not about testing whether you know inverse of matrix or not. See, in all cases, this kind of problems are actually not solved manually. Basically, you write a small program and do it. But the whole idea here is only when you do 1 or 2 problems manually, you understand the steps and your concepts become clear. That's why it is given. So it is not about that you find out the inverse of a matrix in the exam. No, not at all. And I think another point I'll tell
yes,
another.
yes, please.
Please listen to that, because regarding this I told in the last class also. For example, sometimes say a laminate which is subjected to NX, you want to find out what are the mid-surface strains and curvatures. Okay, so
Yes, sir.
It appears that you have to now find out A inverse. So it's not
Yes,
required actually. In the last class I told, I don't know whether you have followed that. Suppose can I share this thing? Just I'll show you. Just bear with me. Yeah, I'll write. Yeah. Somebody asked, but since you are not there, I'll just tell you.
Just for mid-surface strain, we have to calculate the inverse and multiply with n.
No, not at all. Not at all. You just see. Just follow. My screen is visible, right?
Yes, sir. Yes, sir.
Suppose it is like this. It is symmetric, so I'm not writing the other part. Okay, let me write. Suppose you have a laminate which is subjected to only NX. Or only NY, it doesn't matter, okay? And suppose it's a specially orthotropic laminate. Therefore, you have to find out what is the mid-surface strains and curvature. So what this equation comes down to, because NY is 0, NXY is 0, therefore it is only NX 0, 0, A11, A12. This is also because if it is specially orthotropic, this is also 0, and A22, this is also 0, A66, epsilon x naught, epsilon y naught. Because it's specially orthotropic, there will not be any gamma. Okay. Suppose this is 090, specially orthotropic laminate. Okay. Now, if you have to find out epsilon x naught, epsilon y naught, of course you can find out taking inverse of this A matrix. But here actually it becomes a 2 by 2 equations, you know. Nx is equal to A11 epsilon x naught plus A12 epsilon y naught. 0 is equal to A12 epsilon x naught plus A22 epsilon y naught. So you have two equations, two unknowns. From there you can straight away find out. I think even in the assignment also you have given such questions. It is not expected that you spend your time by finding out the inverse, that to manually know. So that's why this kind of problem is given, so that immediately you can find out these two variables without going into much of these things. So you can find out that. Is that clear? This is a short, I wanted to mention that because last lecture, last live session also I mentioned, somebody asked why, no, you are not expected to do that, at least in the exam. And ideally, I told in the class also that basically these kind of problems are not solved, manually. You write a small program where all inverse everything could be actually calculated and the results could be even because the steps are known. But we have solved one or two problems to understand each and every step so that it becomes clear, okay? Each step becomes clear to you. So that is what it is. You can avoid finding out the inverse. Okay, now any something else you are asking, please ask.
Yes, thank you, sir, for this application. And second one, that your lectures and the assignment part is enough to cover the exam portion. Means there is no need to go with another source like.
No. You can always do. See, the whole idea is that in lectures it was not possible to solve many problems. See, this is a course on mechanics of composite material structures. Therefore, it's important that you solve problems. So for your understanding, if you want, I have given the names of the books also, you can solve some extra problems. But for example point of view, I think it's good enough if you have followed these lectures.
Yes, I'm just asking for example because the books that have been given in the course page, that there is no problem with solution. Only a long derivation and all thing, but there is no numerical portion with the solution in those books.
No. I think in cause book the problems are there. I have given AW cause, auto cause. Problems are there. Problems are there in cause book.
And one last question that there is some normalization relative marking in exam like in mostly IIT and NIT. If there is some fixed criteria like for S excellent grade, A grade, B grade, C grade for the students, means if nobody will able to cross the 90, then there is some criteria that they will do some relative marking. So in their exam there is like also no.
Oh, that I think this is guidance. NPTEL has a own guidelines there. So right now I am not able to tell you, but I think it's basically all these things are fixed. How much marks will go from this? How much marks will be from the exam? All these guidelines are fixed already.
Yes,
okay.
There is some guidelines like if somebody will cross the 90 above, then they will get the elite plus gold certificate. So if nobody able to cross the 90, then nobody will get that certificate. If nobody will cross the 90.
So this is done for all the courses across, it cannot be.
Okay.
Oh, yeah.
Means they arrange that type of difficulty level so that some students can crack or get above the level. they design the paper as per the criteria.
I'm sure that is possible. Otherwise, why a grade is there? That is possible.
Yes. Thank you, sir. Thank you.
Yeah. Well.
Now I have. Thank you.
Yeah. Any other questions from anyone else?
Sir.
Yes.
Sir, can you explain this about the special orthotropic regions that where A130Y?
Oh, just a minute. Special orthotropic. That special orthotropic. Here you are telling no A16, A26, why it is 0? Is it this? Are you
Yes,
asking?
sir. Yes, sir.
Yeah. Because
A16.
see, you see what is A. Just go through classical lamination theory. What is A? A is nothing but, suppose you have an n layer laminate. I think you remember that definition of A. Suppose there are n layer laminates, 1, 2, like this, there are n layers. Therefore, sum over all the layers, k going from 1 to n, it's actually q bar k into zk minus zk minus 1. What is zk and zk minus 1? That means suppose this is the reference plane. If you have kth layer, then top of this is zk minus 1, bottom of this is zk. That means for the first layer, this is z0 and the bottom one is z1. This is what the nomenclature we have followed. So this is A matrix, okay? If you expand this is actually, I am writing it like this, k is equal to k going from 1 to n. So this is q11 bar, q12 bar, q16 bar, q22 bar, q26 bar. I am not writing the lower triangle because it's symmetric. Okay, I'll write it. q12 bar, q16 bar, q26 bar, zk minus 1. This is nothing but the thickness of the kth line. Now you see this A, this is actually A11, A12, A16, A22, A26, A66. Now tell me what is A16? A16 will be Q16 for the kth lamina, half for all the lamina, okay, into TK. Is that clear? Now, if you have suppose only two layers are there, one is 0 degree, another is 90 degree. So both are specially orthotropic lamina. Now, what is the characteristics of specially orthotropic lamina? Q16 bar, Q26 bar is equal to 0, isn't it?
Okay.
Similarly for 90 also. Therefore, this will be 0 for 0 degree and 90 degree. Similarly, A26 is also 0 for 0 degree and 90 degree. Okay. So for specially orthotropic lamina means layers are only restricted to 0 or 90. And for 0 and 90, there is a specially orthotropic lamina. Therefore, the laminate is specially orthotropic laminate. Therefore, A16, A26 is 0. If you try to see physically what does that imply, A16 implies if we apply NX, there will be shear strain. If A26 is there, if we apply NX, there will be shear strain. So that means the stress along normal stress along X and Y will lead to shear strain. That means shear extension coupling. But if it's a specially orthotropic laminate, which is made of each layer is special orthotropic lamina, the shear extension coupling is absent. Therefore, A16, A26 are 0. Is that clear?
Yes, sir. Fine.
Yeah. But if you remember, just go back and see laminate. This is also 0 for some other kind of laminate. What is that laminate? If you remember, balanced laminate. Suppose you have a laminate where for every plus theta, there is a minus theta, say plus minus 45 degree laminate. Okay. There also A16, A26 is 0. Okay. So these are some special kind of laminate. But here it is understood. Straight away we can say that because it consists only of 0 and 90, both are special orthotropic lamina for which we know that Q16 bar, Q26 bar are actually absent. That means 0. Therefore, A16, A26 are 0. Okay. Any other question?
Good afternoon, sir.
Yes, I could not see that one.
Sir, I have a doubt. Can you explain the reduced transform stiffness matrix, sir?
Reduced transform stiffness matrix, is it?
Yes, sir.
Okay. Just a minute, I'll just tell you.
Chat box.
No, you just open the screen again. Share the screen, yeah. See, first of all, there are two terms. One is reduced, another is transformed. What is reduced? From 3-dimensional, we have reduced it to 2-dimensional. Could you follow that in the lecture?
No, sir. Because of I am doing job.
No, what I suggest is, see, I cannot derive the whole thing again here because that was a 40 minutes lecture, but I'll tell you what exactly is this.
Yes, sir.
Suppose you have this sigma x or sigma whatever, say sigma 1, sigma 2, sigma 3, tau 2, 3, tau 3, 1, tau 1, 2. The 6 components of stresses are actually, I think I told you just are actually related to the corresponding 6 components of strains. Okay. These are the C12, C13, C14, C15, C16, like that. C16. Actually, it's I'm writing straight away 16. It should be 61, but it's a symmetric matrix that we have already proved. 666. So this is actually the stiffness matrix. In short, we write C. This is actually 6 by 1. The strain is 6 by 1. And this matrix is naturally 6 by 6. Okay. This is the stiffness matrix. We can take inverse of this and we can write strains in terms of stresses. This will be also a 6 by 6 matrix. What is this called? This is called compliance. This is nothing but C inverse. This is called compliance. Okay. Now, this is for a 3-dimension. Now, when you talk about a lamina, actually a lamina is very thin, you know. A lamina, if you just see a lamina, it is very thin. Its thickness is very small compared to its lateral dimension. Okay. Therefore, suppose this is your X, or say, and this is Z. So thickness is very, very small compared to its lateral dimension. Okay. And then it is subjected to only in plane load. That means it is subjected to sigma X, sigma Y, tau XY. And we know the condition for plane stress, considering a 3-dimensional problem, special problem to be idealized as 2-dimensional is, that means there is only load is in plane load. That means the load is acting only in this plane. And there is no variation of this intensity along the thickness. Okay. That means the load is acting only in this plane. Okay. And there is no variation of this intensity along the thickness. And the thickness is very, very small. These two surfaces are free. If I consider this to be H, suppose the thickness is say T. T is very, very small compared to the lateral dimensions. Now at Z is equal to plus minus T by 2, sigma z is 0 because it is free from any out of plane load. And since t is very small, we can consider that sigma z is 0 elsewhere also along the thickness. So that is the basic idea of a plane stress condition. So similarly, even tau xz, tau yz are also 0 going by the same logic. Okay, sigma z is 0. Therefore, a lamina could be actually considered to be a plane two-dimensional problem. And so what we do is now we only consider sigma x, sigma y, and tau xy, and other three components of stresses are not considered. So if we write, suppose we write the epsilon x, epsilon y, epsilon z, gamma xz, sorry, gamma yz, gamma zx, gamma xy is equal to S11, where this is nothing but the inverse of C, S13, S14, S15, like that, S16. This is a 6 by 6 matrix. Okay, and it relates the corresponding 6 components of stress: sigma x, sigma y, sigma z, tau yz, tau zx, tau xy. So these three stresses are not there. Therefore, we can straight away take the compliance only relating epsilon x, epsilon y, and gamma xy. And we can show, please go back and see the slide, that even though epsilon z will be there, but this is not independent. This is a function of epsilon x and epsilon y. Please go back and see the slide. I have clearly explained that. Okay.
Okay,
so,
sir. Okay, sir.
So we can now write this as only epsilon x, epsilon y, and gamma xy as a function of S11, S12, and then 0, or you can write S16, S22, S26, and S66. Okay, sigma x, sigma y, tau xy. So this is reduced. Here we have straightway taken S11 from here. We have straightway taken S12 from here. Okay, so this is reduced compliance. But then we cannot straightway take this as C11 because epsilon z is there. Please go back and see. I have proved that also in that. Okay, so when we reduce this here, we cannot straightway take C11 relating sigma x and sigma 1 and epsilon 1, or sigma x and epsilon x. Therefore, here what we do is we can show that sigma x, sigma y, tau xy is, therefore we change it from C to Q. Because this Q11 and C11 is not there. Of course, they are related. That relation is there. You can just go back and see the slide. It is, the derivation is there. So Q6, Q66. This is epsilon x, epsilon y, gamma xy. I mean, here we have written 1, 2, 3, xyz. Please go, don't confuse, same thing. Okay, so this is xyz. So this is the reduced stiffness. This is reduced stiffness. Okay, now when it coming to a lamina, if you are considering the principal direction, that means where the fibers are there, this is 1, this is 2. So we can actually relate sigma 1, sigma 2, tau 12 is equal to Q11, Q12, 0, Q22, 0, Q66 into epsilon 1, epsilon 2, gamma 1, 2. This is in the material direction 1, 2, in the material plane. Because in the principal material direction, there is no interaction between the normal stress and shear strain. Therefore, these two are 0. Now, when we try to do for a general lamina, where the principal material directions actually do not coincide with the analysis direction. Analysis has to be done in this XY, but the principal material direction do not coincide. Okay. Then what we do is by simple stress and strain transformation, because we have the formula for stress and strain transformation. So we can use those formula, okay, like sigma 1, sigma 2, tau 1, 2 is nothing but stress transformation matrix T into sigma x, sigma y, tau xy. What is this T? This is nothing but a function of theta, sin theta, cos theta. But what is theta? Theta is the angle that the principal material direction 1, 2 makes with xy. Okay. Similarly, we have the strain transformation also. Epsilon x, epsilon y, gamma xy. If we use the same transformation as stress, P inverse of epsilon 1, epsilon 2, gamma 1, 2, but then it should be divided by 2. Okay, so we have the relationship between the stress and strain in the material and in the material axis and the global axis. Now, what is our objective? We want to correlate the stresses in the analysis axis, that is epsilon x, sigma x, sigma y, tau xy, to the corresponding strains, and by this transformation, we can actually show that sigma x, sigma y, tau xy is actually equal to P inverse Q into R, where R is the Reuter matrix, into T into R inverse into epsilon x, epsilon y, gamma xy. Now this T is function of theta. Q is this Q matrix, which is the reduced stiffness matrix. R is, of course, it's only number 0, 0, 1, and 2 numerals. And therefore, this whole thing is actually function of Q and theta. This we call as the reduced transform stiffness matrix. Okay, this we call as Q bar, which is nothing but T inverse Q R P R inverse. If you remember, just go back and see the slide again. See the presentation. R is, I think, 1 0 0 0 1 0 0 0 2. Okay, and T is the standard stress transformation matrix. You can see that sign in terms of sin theta, cos square theta, sin square theta, minus 2 sin theta, cos theta, like that. Okay, so this is called reduced. Reduced means already it is reduced from 3 dimension to 2 dimension, and now it is transformed. What is this transformation? We have transformed this Q from 1 to material axis to xy stiffness. This is what it is. That means using this, we can straight away relate the stresses and strain in the analysis axis. Is that clear?
Yes, sir.
So please, go back and check the derivations again in the PowerPoint presentations in the live that class video. You can see this is already derived nicely there.
Okay, sir.
Yeah. Any other question?
Sir.
Yeah, please.
Sir, I have a doubt. Sir, A is equal to in bracket मैट्रिक्स है, उसमें मैट्रिक्स है, तो इनवर्स कैसे करते हैं सर हम?
that मैं 2 बार बता चुका हूँ ऑलरेडी. अब ये आप थे क्या अभी 10 मिनट पहले?
नहीं मैं नहीं था अभी.
See again, anyway, I am repeating again. Please be, I have told this number of times. आपको इन्वर्स करना नहीं है. This exam you will not be tested. अब हमारा मकसद नहीं है कि आप how fast you can do the inverse. इन्वर्स करने की जरूरत नहीं है. इन्वर्स करने वाला प्रॉब्लम नहीं चाहिए. But you have to do inverse. If you have to solve, suppose nx ny nxy is equal to a into epsilon x naught epsilon y naught gamma xy naught, then you have to take inverse. But for that, you can write a small MATLAB code and do it. But for the time being, for this exam or for these assignments, we have intentionally gave some problems where you don't have to do inverse. Because inverse case, manually you can do inverse. You can find out inverse, but that is not the idea here. You will spend 20 minutes to do an inverse. That is not required. Just now I am repeating again. You don't have to do inverse. Suppose if nx, ny, nxy is equal to a11, a12, a16, a22, a26, a66, epsilon x naught, epsilon y naught, gamma xy naught. So naturally, if this is given and you have to find out this, आपको inverse लेना है. That is the general procedure. Okay, but what you are asking, I understand. How I will do inverse? आपको करने का जरूरत नहीं है inverse. ऐसा प्रॉब्लम नहीं दिया जाएगा कि जिसमें आपको inverse करना है एग्जाम में. But suppose I give you a problem. Say a laminate is there, which is subjected to say only ny. Okay. For the laminate, you know there's a matrix, and suppose this is specially orthotropic symmetric laminate. Suppose, okay, subjected to only ny. You have to find out what is the mid-surface strains and curvature. Now, because it is specially orthotropic, I'm giving you some example that it's very simple हो जाता है. A11, A12, ये 0 हो जाता है. A22, ये भी 0 है. A66, okay. अभी आपको क्या करना है? nx तो नहीं है, nx is 0, ny is given, nxy is also not there, it is 0, and you have to find out epsilon x naught, epsilon y naught, and gamma xy naught. Okay. Now gamma xy naught will be anyway 0, but you can write that gamma xy naught, it will be 0 anyway. Okay. So अभी should you go for inverse? नहीं चाहिए ना, इसके लिए you don't have to do inverse. It's a simple two algebraic equations you have to solve. What is the first equation? 0 is equal to a11 epsilon x naught plus a12 epsilon y naught. Okay. Second equation, ny is equal to a12 epsilon x naught plus a12 epsilon y naught. बस यही दो इक्वेशन है आपको सॉल्व करना है. So इसमें क्या क्या पता है आपको? ny you know, a11, a12 you know. Therefore, two equations, two unknowns, you can find out straight away what is epsilon x naught and what is epsilon y naught. आपको inverse करने का जरूरत नहीं है इसमें. Is that clear?
Yes, sir. But sir, one question, sir. A11 को जब हम इन्वर्स कर दे तो उसका क्या कैलकुलेशन है क्या? A11 को करना है, हमको ए इन्वर्स करना है, निकालना है.
क्यों?
तो A11 का इन्वर्स
नहीं से इन्वर्स का तो निकालने का तो प्रोसीजर है. आई कैन नाउ टेल यू हाउ टू फाइंड आउट द मैट्रिक्स इन्वर्स ऑफ ए मैट्रिक्स. You find out the adjoint of a matrix, okay? Determine the matrix, find out the cofactor matrix, then divide by the determinant. That is how you find out the inverse. This is nothing new, na? Given a matrix up to 3 by 3 you can do by hand. Even 4 by 4 also you can do by hand. It will take time. So how to do inverse? That is known in any elementary plus 2 books. To mil jayega. But what I am asking, what I am trying to make you understand is, in your assignments or in your problems, here we are not testing how well you can find out the inverse. Therefore, we are trying to avoid that you don't have to determine the inverse manually. Agar aapko finally, if you have understood that course, how to analyze the laminate, naturally you have to find an inverse. For the most generalized loading, all these nx, ny, nxy, sab ek saath hoga na. Aisa thodi na hoga ki only ny. So all these 6 components of force and moment resultants will be there, and it will be 6 by 6 matrix. Therefore, you have to take inverse. But for that, you have to write a small code, maybe in MATLAB or any other language. You write a code and you can solve it. But if you are asking me how I will do it in the exam or assignment, that's why in the assignment or exam, the problems are given in such a way that you don't have to do inverse. The objective here is, it is important that you understand the steps. Okay, I assume that all of you know how to determine inverse of a matrix. Okay.
Okay, sir. Okay, sir.
Is there any other question? Yeah, how to practically calculate engineering properties of single laminar. I think I have already discussed these things in detail in the experimental determination of E1, E2, isn't it? Following ASTM standards. See the micromechanics module, maybe lecture 3 or 4, experimental determination of the strength and stiffness properties, where I have given in details. But of course, we do not load a single lamina. We actually make it sufficiently thick following certain standards and then find out. Suppose we want to find out. Yes, that's what. No, it's in. I think I told that also. We take around maybe 6 to 8 0-degree plies to make a thick, and then it has a standard length following ASTM standards, and then we load it in UTM to determine E1. Similarly, when we try to find out E2, we make sure that it is sufficiently thick. Oh, hello, am I not audible? Kaushik, are you getting, could you hear me? Yeah, fine, yeah. So, yeah, so what I was telling is this, you're right, we don't load a single lamina. Even though we say that it is the, E1 is the longitudinal Young's modulus of an unidirectional lamina, but when you do the test in UTM, when you conduct the test in UTM, just go back and see the slides. There are certain standards we follow. Maybe we take 6 to 8 0-degree plies having certain length and certain width. I think if I remember correctly, the width is around 1 inch, okay? And then like 25 mm, and the length is around, it was around 229 mm. And there is a fixture, like we put some tab to grip it well, okay? Then we find out and we say, if we load it along direction 1, we say that from the stress strain curve, the slope of the stress strain curves actually give us E1, and the point at which it fails gives us sigma 1 TU, that means longitudinal tensile strength. Is that clear, Kaushik? Thank you. Any other question? You just see, in this regard, I can tell you, when we have found out the compression strength, longitudinal compression strength of a unidirectional lamina, what we have done, what was done. See the figure which I have given in that lecture. The most of the length was actually constrained. Only a very small length was kept open, because if you subject it to compression otherwise, leaving a larger length, it will buckle. To ensure that it does not buckle, that is how. So finally, whatever is the slope of the stress strain curve we get, we say that it is that is, I mean, sorry, whatever is the final strength we get, that we call it is a sigma 2 Cu. Okay. How to calculate A matrix from Q bar, because in case of laminate there are many layers, so different Q bar matrix. Then how to conclude this different Q bar? No, you just check the formula. You just check the formula, okay? You just check the formula. Yes, that is why it is. There are n lamina. Is it not shared? Oh. Every time it goes, huh? Yeah. So your question is how to calculate A. I think I have explained this in details in the laminate analysis, but again, I'm telling you, I'm not deriving it, okay? Derivation is already there. Suppose this is the reference plane. That means the mid surface, okay? So what is A? A is actually K going from 1 to N. What is N? There are N layers. Okay. Q bar, I think I have explained this just half an hour back, into ZK minus ZK minus 1. This is the definition of A matrix. Okay. What is this? Suppose we consider the first layer. So for the first layer, suppose this is, you are right, Q bar for the first layer will be different from Q bar of the second layer, and it will be different if all the layers are different. They are different in each layer. Okay. So for the first layer, we have suppose Q bar 1. Then from the reference plane, we have the distance, okay, Z0, and then this Z1. Okay. So we can now for all the layers, I can write the Q bar, multiply it. This is nothing but the thickness of the kth layer. Okay. Therefore, A11 is nothing but Q11 bar K sum over all the layer into Tk. Similarly, A12 is Q12 bar for the kth layer sum over K going from 1 to N into Tk. Similarly, A22 is nothing but K going from 1 to N Q22 bar K into Tk, and A66 bar, sorry, A66 is equal to sum over K going from 1 to N Q66 bar for the kth layer into Tk. And as just now I explained, I mean, similarly, sorry, you can have A16 is equal to K is equal to K going from 1 to N Q16 bar K Tk. A26 is equal to K going from 1 to N Q26 bar K into Tk. I think I have done all A11, A12, A22, yeah, all the 6. So this is how you calculate A matrix. For that matter, this is how you calculate B matrix and D matrix. Is that clear? Yeah. So any other question or? Yeah. So I think it's time. Just somebody is typing something. Let me just check. Any student is typing something?
Speak also.
Okay, I think if there is no other question, it's already time. So we'll have another this thing before
Suppose this session exam is coming.
exam is coming. Then okay, I think I wish you all the best for the exam. I'm sure all of you will do well. Okay, please follow the notes, and again wishing all the best for the exam. Thank you. Yeah.